Good evening and welcome to tonight's special event. Hi, I'm John Beacom. I'm the director of the Center for Cosmology and Astroparticle Physics, or CCAPP. The mission of CCAPP is to discover the universe and its wondrous contents, to train our students and postdocs on the cutting-edge research techniques needed to do that, and then to share the results with the public. A really important part of how we do that is this lecture series itself, which is the R. Jack and Forrest Lynn Biard Lectureship, and it was endowed by Captain Forrest Biard, who was an alumnus of Ohio State University, and he also served in the Navy during World War II, closing out in the rank of captain. You can read about him on our webpage. He played a very important role in code breaking and then the decisive victory at the Battle of Midway. He was very interested in cosmology and astroparticle physics and very interested in the idea of sharing science with the public. One of the things that I've heard about and I've never actually seen is he used to have his own TV show called Mr. Wizard, where he would do physics demonstrations. And if anybody can find footage of that somewhere on Betamax or something, I would love to see it. Now, this is a special Biard lecture. This is the 16th one. And during those previous 15, we had outstanding speakers from all around the world. But tonight is something special. Tonight is the first time that we had someone from our own CCAPP group. And the reason we're doing this is because we decided collectively that we really wanted to honor the contributions of our speaker, Professor Honscheid, and we unanimously chose him for tonight. So Klaus had a very distinguished two careers. His first career, you may not know about, began in, first 2 decades were in high energy physics experiment. And then at some point he decided to do something very daring, which is switch careers completely and start working on cosmology experiment, where he spent another couple of decades. This is not an easy thing to do. But both of his careers were very successful. He made this switch at the beginning of CCAPP about 20 years ago. And he was instrumental at that time in getting us into the first of the big dark energy surveys literally called the Dark Energy Survey. Not a super creative name, but what can you do? And over these 20 years, he had leading roles in both the Dark Energy Survey and the Dark Energy Spectroscopic Instrument. He'll tell you about both of those tonight. But I want to highlight that Klaus's success is CCAPP's success. The things he did in those experiments and working closely with our students and postdocs helped CCAPP as a whole rise to international prominence and helped us attract lots and lots of great people. And we're all grateful for Klaus's role in that. We're also grateful for your interest in being here tonight. There are something about 400 something people here tonight. I recognize a lot of familiar faces from previous years. That's great. I hope you keep coming back to see us. Now, without further ado, let's welcome Professor Honscheid.
Okay, thanks, John. Okay, I think that microphone is on. You should never be in the room when somebody introduces you. That's always so embarrassing. Okay, well, good evening, and thank you all for joining me here for the next hour or so as we try to explore some of the mysteries of our universe. Now, the universe itself, I don't think needs much of an introduction. We all have been sitting outside at night, staring at the sky, looking at the stars. If you're lucky, we see the Milky Way and those constellations that nobody can ever find. But even with we might have to turn this microphone off here. Even with really good conditions, which we really never have, you can see how many? A few hundred, maybe 1,000 stars. To see the universe in greater detail, you need a telescope. And then you zoom in a little patch like this one, and then the entire beauty of the universe, of the cosmos, is revealed. There are 100 million stars in our Milky Way, our own galaxies. There are 1 trillion or more galaxies in the observable universe. It is a really, really big place. These are two of the telescopes we use to take images like this one. They are going to be the stars of our story tonight. On the left, the Mayo telescope on Kitt Peak in Arizona, about an hour west of Tucson, and on the right, the Blanco telescope on Cerro Tololo in the Chilean Andes. So our story begins in 2006. That was a special year for cosmology, because a bunch of things happened that year or around that time. Of greatest importance, of course, was the discovery of dark energy. That was just a few years earlier than that. We will talk about this. And everybody was eager to learn more about it. That means there was support from the funding agencies, from the national laboratories, from the universities, and our own CCAPP, as John already mentioned, was founded that very same year. And secondly, a little bit less known, there was also some change in the particle physics community. Several experiments were ending or shutting down in preparation for the Large Hadron Collider that is now operating in Geneva in Switzerland. Not everybody wanted to work on these, at the LHC, so a large pool of very talented scientists with a great deal of experience in instrumentation and large-scale projects became available to join forces with the astronomers. And then lastly, but not least, around 2006, many in the astronomy community have moved on to newer and larger observatories, making first the Blanco and then the Mayo available for new instruments and new challenges. So the events of 2006 first led to the, if this clicks, here we go, one too many, the Dark Energy Survey experiment, and then a little bit later, the Dark Energy Spectroscopic Instrument. These are two very large sky surveys, and how these two experiments became the most, or some of the most exciting experiments in the recent history, that's the story I'm going to tell you tonight. And before I start or continue with this, let me apologize right away for the obvious lack of creativity in our community. And how could we name these two experiments DES and DESI? Anyways, so to understand what these experiments are doing, a little bit of background knowledge in cosmology is necessary. But don't worry, we can do this without many equations. What we're going to do is we're going to look at three major observations, and understanding those will help you to get an idea what DES and DESI did. We're going to start with the expanding universe. If we look into the deep cosmos, we notice something very profound. Almost everything around us is moving away from us. Edwin Hubble in 1929 was the first one to realize this trend. This is data from his original paper. He looked at galaxies nearby around our Milky Way, and he found that almost all of them are moving away from us. Here is a newer, more modern plot of the same data, of the same concept. Now, you can clearly see that with a larger distance, maybe you can actually see this pointer here. Let's give it a try. No pointer, it's not strong enough. When the distance goes up, the velocity at which the galaxy is moving away from us goes up as well. In fact, this is a very simple relationship. It's just a linear relationship. The velocity is directly proportional to the distance. That is the famous Hubble law, and the proportionality constant is the Hubble constant, h0. Today, it has a value around, we're not exactly sure, of about 70 kilometers per second per megaparsec. Now, megaparsec is a distance unit that we use a lot in cosmology. It is a very, very large unit. It's about 3.2 million light years. To give you an idea or something to compare to, our entire galaxy, the Milky Way, if we express its size in megaparsec, it's something like 0.03 megaparsecs. So this is a big unit, but we're also going to use it to explain the big universe. So what does Hubble's law mean? If you have a galaxy at 1 megaparsec, it's moving away from us at 70 kilometers every second. If you have another galaxy at twice the distance, its recession velocity is twice as large. So now it's very difficult to visualize the expansion of three-dimensional space. So let's drop down to 2 dimensions, and you imagine that the entire fabric of the universe is mapped to the surface of our balloon here. And then we take some galaxies and put them on the balloon. Those are the red dots. And then we see what happens. Let's watch it for a moment as the universe expands, as the balloon inflates. You will notice that the dots, our galaxies, are not growing. Gravity holds them together. But the space in between is stretching. And if you were a tiny astronomer living in one of these dots, let's say here, and you look around, you see all the other dots moving away from you. And if you look at the dot further away, it will move away from you even faster, Hubble's law. So how do we know that this is really happening? We know because we know how this expanding space affects light. So light travels through space as a wave, and we have marked here a wave like this one. You can see this traveling from one galaxy to another. Now, let's say this is a blue wave. It doesn't matter. And then as the distance in galaxies is large, so a wave travels for, I don't know, millions of years, billions of years, all while the fabric of space is expanding. So watch the wave here, and you already see that it's stretched with the expansion of the universe. So in physics, we know if a wave is stretched, it moves towards the red end of the spectrum. So we call that the redshift, or in this case, more precisely, the cosmological redshift. And this is what we can measure with our telescopes. We can measure the wavelengths as we observe it. We know the wavelength as the light was emitted, and that gives us what we call the redshift. And then we multiply it with the speed of light to get the velocity, and then we use Hubble's law to get the distance to this galaxy. So, because it takes the light so much time to reach us, it means that looking back at the distant galaxies, it's like looking back in time. We see the universe how it was at a much younger age. And if you go all the way back in time, 13.8 billion years, since the universe is expanding, it was smaller in earlier times, and if you go all the way, it was a singularity. That's the Big Bang. And today, our balloon, our universe, has, thank you, Christine, has perfect timing, has reached a size of, well, whatever that is now, but the real universe has reached a size of about 93 billion light years. Okay, so we now know, and we have seen, the universe is expanding. But what about those galaxies that we put on there? What is holding them together? Where do they come from? To understand this, we have to look at another major observation from 60 years ago. And to understand what's going on, look at this animation here of our solar system. In the solar system, almost all of the mass is right in the center. That is the sun. And then we can show and understand that the inner planets whip around much faster than the outer planets. And for the longest time, for decades, we have assumed that the same is true for galaxies. So we assumed that the galaxy, you have this bright bulge. We assume that's where all the mass is. And then the outer stars, just like in the solar system, they move slower and slower. Now, that's not real. The real galaxy moves like this. And you see that the outer stars move about the same speed as the ones further in. In the 60s and 70s, Vera Rubin, a famous astronomer, actually measured the speed of these outer stars. And what she found is basically impossible. The stars are not slowing down. They just flatline, like in this diagram here. So they have sort of like a constant speed. Some of the stars she measured were so fast that they should actually fling themselves right out of the galaxy. So how is that possible? So there must be something that we don't see that has an incredible mass and that has enough gravity to keep those stars bound to the galaxies and affect their motion. And it's actually not too difficult to understand that it's possible there's something that you don't see that affects the motion of objects, of stars. I have two bottles here with my fake stars in it. So this bottle is empty. When I tip it over, the stars will move. And I'm sure you all have an idea how they will move. They just fall down. Okay, no surprise here. Here's a bottle that has the same number of stars in it. If I tip that over, the stars also move, but they move very differently. There's something in this bottle that affects the motion of the stars. Now that's just water, but the same principle applies to the rotation curves of other galaxies. There's something that keeps them in place. And that something is what did I do with my clicker? That something is what we call dark matter. And it cannot just be in the center of the galaxies, it has to be stretched out in this large invisible sphere covering the entire galaxy and beyond. We call that a halo. And we call it dark matter because it doesn't interact with light, not dark halo, dark matter, because it doesn't interact with light, it doesn't reflect light, light goes just straight through it. And it only interacts with the rest of the universe via gravity. Now, dark matter is not only responsible for holding the galaxies together. In fact, it holds the entire universe together. Dark matter is the invisible scaffolding of our entire universe. Okay, so now we actually have the beginning of a model. A model that can explain some of the observations that I showed you, and a model that can make predictions. So in science, it is really important that when you have a theory, you need to test it. You need to verify those predictions experimentally. So in this context, take a look at this imaginary conversation between a graduate student and a professor in the late 1990s. So the student is obviously very excited about cosmology, and he comes to the professor and then asks, is there anything exciting I can work on? Do you have a project for me? And the professor replies, yeah, of course, we have this model that we are trying to understand. It makes lots of observation, explains them, it makes some prediction. For example, that the universe is expanding, but at a rate that is decelerating. Do you want to work on this? Says the student, not totally convinced. Now, this universe is full of all the stars and the galaxies, all this matter. Now we just added dark matter to it. So there's this enormous amount of gravity that tugs everything back together. So obviously, the expansion rate must go down. So why should I bother? So we don't know whether the student took that project or not. If they didn't, they missed out on arguably the greatest discovery of the last century. Now, admittedly, this is not an easy problem. It is very difficult to measure distances at cosmological scales in an expanding universe. You already know about the redshift, but we need a calibrated measurement of some physical quantity. If we had such a standard, we could measure the size or property of the standard at different times in the universe as it develops, as the universe is expanding, and then compare that to our model. Fortunately, nature gave us such a standard. Supernovae are exploding stars. When they explode for days or maybe a week, they shine so bright that they outshine the entire host galaxy. There are different types of supernovae. Some of them are called type 1a, and they are the special ones that we need because we understand the underlying physics, the mechanism that makes them go off. And because of that, we know their luminosity, their brightness when they explode. And if we know that, and then we measure the flux, how much light we receive in our telescopes, we can use the simple inverse square law to get to the distance. Okay, so that's the plan. But how do we find these supernovae? They don't happen every day. Well, for that, we look at the same patch of the sky over and over again. and we are waiting for a really bright spot to show up. You see two images of the same area of the sky. The lower one just shows a bunch of galaxies, and then on the upper one, there's a supernova, a very bright spot at the tip of the yellow arrow. Okay, so we have a plan, we have a method to find them, and then in 1998, two teams independently used these exploding stars to measure the expansion history of the universe. So they were completely set to find or to measure accurately the rate at which the expansion of the universe was slowing down. What they found was the exact opposite. When they looked at the data, those faraway supernovas were much fainter than they should be. And the only explanation is that their light must have traveled to us over a much larger distance than was expected. To understand what this means, we can look at this plot. This plot on the vertical axis shows you the size of the universe relative to today. Today is that little pink line in the middle. And on the x-axis, you have the age of the universe in billions of years. So what we expect is that, okay, it's filled with matter. Yeah, we know it's expanding, but gravity pulled everything back, so we expected something like this dashed red line, that the expansion slows down over time. What the supernova actually told us is the blue line. Early in the universe, on the left side of the plot, it is indeed decelerating. But then something happened like 5-6 billion years ago. You see the blue curve bends upward. The universe, the expansion rate is not slowing down, it's accelerating. There must be some sort of substance, invisible again, in every bit of empty space that pushes the universe apart. We have no idea what it is, but we gave it a cool name, dark energy. Okay. Well, we don't really know what it is, but maybe we can at least integrate it in our model. Maybe we can describe the effects. And for that, we have to see what's available, and our best mathematical guess goes back to Einstein, who had in his equation something that's called the cosmological constant. This constant is an intrinsic an energy inherent to the actual fabric of space. It is constant. That means it doesn't change even as the universe is expanding. So if you take some volume, like a cubic meter, the amount of dark energy stays the same in there, whether the universe is growing or not. And that is interesting because look at the plots on the side. This is a very unusual behavior. So the green line, the horizontal line, that's dark energy. Over billions of years in the universe, it doesn't change. It's constant. Now, that's not true for the other components of the universe. Radiation and matter, including dark matter, there's a certain supply, and when the universe gets bigger, the volume gets bigger, and then the density goes down, as we see in the plot. And something interesting happened a few billion years ago, marked by this yellow circle. Then the matter density in the universe dropped below the energy density for dark energy. And that is the time when dark energy took over and the expansion of the universe began to accelerate. So that matches actually with what we see, so that's nice. You can also show in general relativity that a constant energy density means negative pressure. Now, negative pressure, but we can call it repulsive gravity, something that pushes everything apart. Okay, that also matches. So far, so good. Then we can actually measure the energy density of dark energy, and it comes out to be an incredibly small number. In a cubic meter of space, the energy density is a tiny, tiny, tiny fraction of a joule. Or maybe, to visualize this better, it would be like having the energy equivalent of maybe 2 hydrogen atoms in this otherwise empty space. Or if you prefer food measurements, it's about 1 trillionth of a calorie. Dark energy is not very filling. But that's where physics breaks down. We know from quantum mechanics that even empty space is not empty. It's bubbling with virtual particles. So there's something we call the vacuum energy. we can calculate this. And when we do this, we get a number that turns out to be 10 to the power of 120 times larger than our cosmological measurement. This is very likely the largest discrepancy between theory and observation in science ever. Okay, so we accept that, and we don't know what dark energy is, but for sure we know it has to be there. Okay, so let's see if we can put this all together. Over the last century, we have developed a timeline of the universe. We call that the standard model of cosmology, or lambda CDM. Lambda, that is the Greek letter lambda we use for the cosmological constant, and CDM stands for dark matter. It begins on the left with the Big Bang, followed by a period of rapid expansion. And then, over time, the hot primordial plasma cooled down, and after about 380,000 years, the temperatures were low enough that atoms could form. At that time, the radiation, the light, the photons were no longer trapped. They could escape and stream freely. That was the first light in the universe. Today, we observe this as a cosmic microwave background. We can actually measure it. Then, over billions of years, the invisible dark matter took over, building the scaffolding of the universe, attracting matter and other matter to form the large-scale structure in the universe. And then towards the right, you see the bell shape is flaring outwards. Dark energy is at play, expanding or accelerating the expansion of the universe into the future. And if we add up all the pieces to make this model work, we turn it off and back on again, and we get this cosmic pie chart, which is profoundly humbling. Everything we can touch or see, the planets, the galaxies, they just make up 5% of the universe. The other 95% are a total mystery. 27% of it is dark matter holding the galaxies together, and 68% is dark energy trying to push the universe apart. Okay, so now you should ask, if that's our model that can't explain 95% of the universe, why should we even bother? Well, there's a good answer, because the model works incredibly well. Let me show you. I talked about this first light, the cosmic microwave background. When we measure this with our best instruments, we reveal a pattern of tiny temperature fluctuations. They're really tiny, like 1/10,000th of a degree. And these patterns are not random. There's a rhythm to these patterns. There is some structure to it that we can measure. And if we measure this, we get a plot like this. Now, the details of the plot are not important right now. I want you to focus on the red dots with the arrow bars. These are the actual measurements of the Planck satellite. And that solid line weaving through all the plots, this is not an after-the-fact fit. It is a mathematical prediction of our model. And it describes the data incredibly well. So the model actually has a lot of benefits. Okay, now let's see. I turned it off again. We have this model. This can explain, let's say, the cosmic microwave background very well. But that's 14 billion years ago. A real theory, the ultimate test for a real theory, is that it can predict what comes next. Can this model predict the universe today in which we are actually living? Okay, so let's see. Remember those tiny fluctuations in the microwave background? Those were the microscopic seeds of all the structure we see today. Over billions of years, gravity has pulled in matter and dark matter into these overdensities. The gas compressed, it ignited, it formed the first stars and then the galaxies. But at the same time, on the other hand, dark energy is trying to push everything apart and increase the space between the galaxies. So we have this epic cosmic tug of war between gravity and dark energy. And the shape of the universe today depends on the outcome of this tug of war. Did gravity win and form a very structured, very clumpy universe, maybe like the last cube here on my slide? Or did dark energy dominate and pull everything apart, smooth it out, making a much more diverse universe? Our model, this standard model, is so precise that we can actually calculate and predict how the universe should look like today and who won that battle. So this here is a mathematical prediction using only the information from the early universe, from the microwave background, and then predicting how the universe should look today. Now, on this axis here, I call it clumpiness. Physicists call this the parameter S8. That doesn't really matter. For right now, it's just a score of clumpiness, how structured the universe is. And the prediction is that in our universe today, if the model is correct, that clumpiness should fall into this red ellipse. Now, that's something we could measure and validate our model. Just to give you an idea how complicated this is really difficult. It's like I give you a picture of a baby, and then I'll ask you, just looking at this picture, to predict the size, the weight, the hairline of the same person 6 years later. Well, that's actually what our challenge is. That's what we are trying to do. We take a baby picture of the universe and predict the grandfather universe with this. And to do so, to see if we are right, we had to build a brand new instrument, something that can take pictures of the universe as it's evolving through time and then answer this question. And that gets us to the Dark Energy Survey. This is the Blanco telescope that I showed you before, and this time we look inside. So you see the telescope and this big black cylinder on the top. That's where we put our new instrument in there, a gigantic digital camera. We call it Dark Energy Camera. We are not very creative. And it's really big. It was the biggest camera of its type at the time. To give you an idea about the size of this camera, let me show you. This is a lens. This is the entrance lens of the optics. It's more than 3 feet in diameter. Actually, it turns out that polishing something that big and getting the glass is not only very expensive, it takes a long time. So it was incredibly important that in 2006 and the next years, we got support from CCAPP to actually make this happening, and get the survey underway. Oh, I have more plots to show you the size of the camera. This is a shutter. So the shutter is the size of a grown man. Now let's take a look at the camera itself. So this is the camera. You see what we call the focal plane. These are the imaging sensors. They are charge-coupled devices or CCDs. It's not exactly the same you have in your camera today, but it's the same idea. Altogether, it's 570 megapixels. So it's still a pretty impressive camera. What is special about this camera is also its wide-angle optics. So with a single exposure, we can capture a large area of the sky. Here's one of these exposures. And in a single one, we can get about 100,000 galaxies. Now, this is not an exposure how it comes out of the camera. This is already processed, multiple images put together so you can see the colors. The real images are a little bit more boring. They are grayscale. They look like this. But what I like about this picture is that little green rectangle on the top that I hope you can see. By the time we built this camera, the state-of-the-art in cell phones was the iPhone 4. Remember that, iPhone 4? And it had a really exciting camera, and its imaging sensor was the size of the green rectangle. That gives you an idea how complicated this scientific experiment was. A great device. So we built the camera, we got it all to work, and then we start our survey. So the idea is to map as much of the sky as we could systematically. So we went ahead and we made exposures, and then we covered more and more of the sky. And before any one of you says this doesn't work, I admit we opened the dome shutter for normal exposures. So this took several hundred nights over 6 years. It was amazing. We got so many people from the collaboration to go down to Chile and observe and enjoy the beautiful night sky. So here are the happy faces. Now that's the chicken. So the story is that we at Ohio State, we took on the project to make all the different elements of the camera work together, the control system and all this stuff, and also the interface for the observers. So in the beginning, we had to debug all this stuff, and well, whenever something goes wrong, the chicken. We had a whole barnyard full of animal sounds, but the chicken was the worst. And I mean, I really, I need to apologize to my wife, Corinna. I'm a sound sleeper, and every time the chicken went off in the middle of the night, she woke up first and had to wake me up. So I'm sorry, Corinna. But I didn't do this alone, of course. I had great help, and Elliot, our software engineer, did all the work. And then, if neither of us could be at the terminal in the middle of the night, my cats took over. They enjoyed sitting in front of the computer and starting to type and chatting with the observers. Okay, very good. So now what we do with all this data? So it's time to get into the science. What we want to do is we take this data and the camera and measure the structure in the universe and come up with the clumpiness today. Remember, we want to compare that to the early universe. And to do this, that sound means there's a mistake. Can anybody guess? Well, we built an optical telescope. And I told you before that dark matter is completely invisible. So how on earth can we take an image of dark matter with a telescope? To answer these questions, we have to call for help, and we bring in Einstein. This is Einstein's masterpiece, the field equation of general relativity. I'm not going to ask you to solve it today. I just want you to look at the two sides. Einstein realized that space-time depends on the stuff that's inside, all the content, the matter, the dark energy. Or in the words of John Wheeler, space-time tells matter how to move, and matter tells space how to curve. Maybe that's still not clear, so maybe let me show you. So let me show you what this means. And for that, we have to see if our camera begins to work. And if not, we'll have to improvise. It works. So what you see here is this black surface. So we use it as a camera because otherwise you can't see it. And think of this as the empty fabric or the fabric of empty space. And when I take a ray of light, like this beautiful white little things that you got when you came in here, and I roll it over through the empty space, what happens is it just rolls and gets lost in a straight line, just as you would expect it. I have another one, Christine, thank you. But we know that space is not empty. So let's put in a galaxy. I have galaxies here. Here's my galaxy, so let's put this in our space. And I will see if you can see this. And you know that it's not just the galaxies. Every galaxy has a dark matter halo around it. So I have my fishbowl, that's the dark matter halo. So we put that down here as well. And then we see what happens. So I'm not sure you see it in this perspective, but you can see underneath here, our space is now completely warped and distorted. That's what matter does to the fabric of space. That's Einstein stuff. And when I now take my light coming from a distant galaxy and have it travel through this space, the light still thinks it goes on a straight line. But because the space it travels through is warped, the light path is actually bent. Just watch. You see it curves. Oh, it's lost again. It curves. We call this gravitational lensing. And we can use this for our measurement. So this is the same principle. Now I have a background galaxy far, far away, they are number 1. Its light travels to us, to the observers. You see our little telescope down there, where we receive the light. But right in the middle of the path, there's this cluster of galaxies and this massive invisible dark matter halo around it. So as the light travels through this massive gravity well, it gets bent, just like the ball got deflected in my demonstration. And this is not just theory. We can actually see this. We can point our telescopes to the sky, and we can see those images, just like the one over there. Do you see those weird, stretchy, fuzzy arcs on the side? Those are the images of the background galaxies. They're completely warped by the matter, the dark matter, the light had to pass through. And this is the secret of the dark energy survey. By measuring the shape of these distorted background galaxies, we can reverse engineer the mass and figure out how much matter exactly, how much dark matter exactly that light had to go through. So we can't see dark matter, but we can measure its effects on background galaxies and use this one to determine the amount of matter in front of these galaxies. That's how we see, in quotes, dark matter. Okay, now this is not easy. The picture I showed you was picked to show an extreme effect. The real galaxies we are trying to study in this survey are not distorted into these arcs. What we actually want to do is we want to see the difference between those two galaxies in the red rectangle. That's the original galaxy, and that's one that is distorted by this gravitational lensing. It's a tiny effect. It's a 1% effect. And what we see in our detectors is what's in the green box, because we have to see this galaxy through the atmosphere, through our optics, and then the detectors are pixelated and there's noise, and that's what we get. So the challenge is to take the image in the green box and figure out what is the difference between the two in the red. Oh, by the way, we don't even know the shape and size of the original galaxies. Every galaxy is different, so all we know is some average distribution of the ellipticity. So clearly this has to become a statistical analysis. We have to look at millions of galaxies to extract the information we want. So somehow I want to impress on you that this is really difficult. And I didn't know how to do this. I think the best way is to use this diagram here from my colleague Jesse Moore that just shows you all it takes from the pixels to the science papers. It is really complicated. The strategy is straightforward. What you need is you need a group of really smart people dedicated to do this work for many years. That's the Dark Energy Survey collaboration. And then you need to find a way to take the shape of these images and turn it into something that you can actually compare to your model. We talk about two-point statistics and correlation function and all this stuff. So once you have this, then you can plot your data, your measurements, in plots like this one. So you see the black dots that represents our measurement. And then you take your model and you vary the parameter you're trying to measure, and you see you get all these different curves. And then you just do this until you get the best fit, and that's your measurement. Okay, again, a lot of work, many, many years. And just to show you that this is real, these are the actual results from a measurement of this gravitational lensing from the Dark Energy Survey they published just a couple months ago. I'm not going to go into any of the details. If anyone is interested, there are many interesting papers and lots of results from the collaboration if you follow this link. We want to go back to the challenge I started. Can we describe the universe today in this clumpiness? This is the plot I showed you before, the prediction from the cosmic microwave background. And here are the DS data. Now that doesn't look too good. So at first you notice the blue ellipse from DS is much longer. But that's in the direction of the second parameter in the plot, the matter density. That is actually not relevant for our question. we just can't measure it that well. So let's ignore this if you can. When you look at the height of the plot, it's about the same, the width of these two shapes, meaning the two experiments have sort of like the same predictive power. Okay, but they still don't overlap. So if you have a situation like this one, you either question your model, or if you're lucky enough to have other data available, you see what other experiments do that measure the same stuff. And that actually turns out to look like this. So these are other experiments doing the same measurement. No, it doesn't look so bad anymore. Well, there's still some scattering around, but it looks like, well, yeah, maybe it's all sort of like coming together. And you get the same impression when I show you now the final results from the Dark Energy survey, because they measured this in many different ways, and then they combined all the results, and that looks like this. In blue, the prediction from the early universe, the CMB, and in orange, the measurement of the current universe. They still don't overlap, but they are getting close. And there are different opinions in the field whether this is a real issue or whether this is actually good enough. I'm in the latter camp. I think this is good enough, and I'm willing to give Lambda CDM a passing grade. So we pass this, sort of. Okay, let's do another test. Let's really convince ourselves that our model is correct. Because what we did now, measuring how galaxies and clusters of galaxies form, the growth of structure, is just half of the story. This competition, this tug of war between gravity and dark energy is also in play when it comes to the overall expansion of the universe. So wouldn't it be great if we could measure the expansion history of the universe directly? And just like we did with the supernova, we need another calibrated standard, something where we know the physical size. And once again, we are lucky because it exists. To make you understand what it is, we have to go back to the early universe. Here we go. And this is now the universe. Yeah, it's an animation. Just a second after the Big Bang. So at this time, the universe was an incredibly dense and incredibly hot plasma with all these particles, protons, electrons, baryons, whatever you name it, dark matter, and in particular radiation, just flying around and bumping into each other. That's my visual for that. Okay. In any sort of like fluid, you always have slight overdensities and slight underdensities. So this peak here in the middle of my animation, that's an overdensity. Very tiny, but it's where we have slightly more matter in it at this moment in time. So what happens next? Well, if there's more mass in it, there will be more gravity, so it begins to pull everything from the region into this center peak. But on the other hand, we have this radiation, we have these photons zipping around like crazy, knocking the particles back. So we have this give and take between gravity and radiation pressure. This is actually, it sounds strange, but it's actually very similar to the sound, my voice. My vocal cords move and compress the air, make it move forward and backwards, and then the elasticity of the air tries to get in equilibrium again. And what is the result? It's a sound wave traveling from me to your ears. And it's exactly the same that happens in this early universe, in this hot plasma. This back and forth causes a sound wave that travels outwards from that overdensity. So if I get this animation to work, we should see this. And is it running? Here we go. That's the sound wave going outwards. Now, this is the blast of baryons, protons, and so on, and radiation that moves outwards a little bit faster than my speed, like more than half the speed of light. And this goes on for a long time, for 380,000 years. And then if I let it go, something happens. At this time, 380,000 years, the universe is cold enough that plasma cools down, atoms can form, and the photons can stream away. So we no longer have this radiation pressure. The sound wave immediately loses steam and freezes in space. So what we are left with in the early universe is a peak in the middle. Remember, dark matter doesn't interact with light, so all the dark matter stays in the middle. And then the shell of baryons outside frozen at a certain distance. Since we call this a sound wave, the size of this wave we call the sound radius or sound horizon. Now, in the universe, of course, there are a gazillion of these overdensities, so I can't do this, but I have more of them. It starts from the beginning. I apologize. Keep on going. Yeah, freeze out. And here we go. Now there are all these overdensities. They all start their sound waves at the same time, a second after the Big Bang. And they all freeze out at the same time. And that creates this pattern, you can imagine, of overlapping valleys and peaks, and then the peaks in the middle. And this is actually what gives rise to these tiny speckles in the cosmic microwave background. So we understand this. And if we analyze the cosmic microwave background, you saw the plot on the right before, that first peak in this diagram is directly related to how far the sound wave was able to travel before the photons freezed out. And we can measure this very accurately, and that gives us a known physical distance in the early universe. We know the size of this sound horizon. We have our standard ruler. So now the question is, what good does it do when this only happened in the early universe? We need to be able to see this standard ruler in today's universe. So let's continue the story and watch what happens next. So then over the next billions of years, the gravity pulls matter and dark matter into these inner peaks, and the outer circles, they're already gone. That's where the galaxies and the stars form. And then, let me stop it here, we end up with a pattern of stars and galaxies that looks like this one. So the question is, can we somehow find a shadow or an imprint of the standard ruler in this picture of galaxies? And remember what I told you earlier, that galaxies form preferably when there's an overdensity. That's just the shell and the center. And if that's true, we should be able to measure the separation between all these galaxies, and there should be a preference for a separation that corresponds to the sound horizon. Not the size it was in the microwave background, because the universe expanded, so it will be much bigger. But we should see this. So what we need to do is we take every single pair of every possible galaxy, measure the separation, and put it in this plot. And then we should see if there is a bump somewhere, which then would be that preferred separation. That would be the size of our standard ruler today. Well, let's have this process continue. Are you continuing? We are not continuing. We are continuing now. Are we beginning from, it's so exciting. Come on, move. How do I make you move? It's so tiny here. Oh, I want you to see this. I don't want you to see that. How can I make this move? Glasses. Oh, here we go. And can I fast forward? Because we have seen this. Here we go. Okay, now I let it go. So I talked about finding these galaxies and taking all the pairs you see like in this animation. And it will go faster, don't worry. So we do this, we put this all together, and then we see a distribution showing up. And in the end, it looks like this. So there's indeed a bump. That's the preferred separation of the galaxies today, and that is the size of the sound horizon, our standard ruler today. So we can actually measure it. Since these were sound waves, acoustic sound waves, and they involve baryons, we call this baryon acoustic oscillations, or BAO. Okay, very well. So now we can develop a plan to actually measure this. What we need to do is we need to create the largest possible map of the universe. And then we slice it into segments, and then for every segment, we look and try to measure the size of this standard ruler, and then we compare it to the prediction from the model. Since the universe expanded, our standard ruler grew massively, and the size today in our current model is about 150 megaparsec. I told you how big that is. So to make this work, we need a huge amount of galaxies. We need a very large survey, and that is what the DESI experiment is designed to do. So we're getting to our next experiment. This is a picture on the inside of the Mayer telescope. It looks very similar to the Blanco because they're sister telescopes, and just like we did before, we are replacing the instrument at the top in this black cylinder with something new. But this is not a camera this time. The name of the survey gives it away, spectroscopic. To actually do the work we want to do, we're not going to take images, we have to measure spectra. So let me explain to you how we measure, how do we create a map. Two coordinates of the three-dimensional map we get from imaging. We already talked about this. The third coordinate we have to measure with the spectrograph. So the spectrograph measures or allows us to measure shifts in wavelengths. Remember, that's the redshift. And once we have the redshift, we use Hubble's law to calculate the distance. And then we get the 3 dimensions or 3 coordinates for our map. Now, there are different objects in the universe. You see some examples here, and you see their spectrum, function of the wavelengths. And all of them have some features, emission lines or absorption lines, that we can use to measure the shift in wavelengths to get an accurate redshift. So that's what DESI is doing. So here, in a nutshell, this is how it works. So we have this galaxy, billions of years away, sending its light towards our telescope. And the telescope, the mirror, focuses its light from the galaxy onto a tiny optical fiber. That optical fiber then, over 40 meters, transfers the light into a special room where we have 10 state-of-the-art spectrographs that break the light down by wavelengths so we can measure the spectrum. These spectrographs, major components of spectrographs, were actually built here at Ohio State in Paul Martini's lab. But let's go back to the focal plane, the actual heart of DESI. Let me just give you an idea. The diameter of the optical fiber is about 100 microns. That's more or less the size of a human hair. So what you have to do is you take your hair, if you hold it up into the sky and hold it steady for 30 minutes at exactly the right position to capture the light that was sent out by this galaxy 10 billion years ago. That's what we are trying to do. That is fun. And then we have to do this very efficiently. I told you we have to make the largest possible map. So we need many, many of these galaxies and their spectra. So we need to do this really quickly. And taking a spectrum takes much longer than just taking an image. It takes about 20 to half an hour per exposure. So what we do is we don't just have one single fiber. We have 5,000 of them in the focal plane. So we get 5,000 spectra at once. And then we also have to be very efficient when we move around. Because when we flew the telescope somewhere else and observe this field, the galaxies we want to look at are in completely different positions. So the fibers all have to move and be accurately positioned. Very difficult. So here's how this was done in the past. In the afternoon at this telescope, some person took these fibers and put them around in specially made plates, and then we use those and image the sky. That is not the fastest way to do this. It was very slow, and then each of these plates can only be used for one single position. So in DESI, we do it differently. We actually have 5,000 robots. Tiny little robots the size of a pencil. They have 2 motors in it that turn 2 axes, and at the tip of the robot, there is the optical fiber. And we can move this optical fiber anywhere in about 1 centimeter radius, patrol radius, and position it on the galaxy we want to observe. And whenever we flew the telescope to a new position, at the same time, we start this orchestrated dance of the robots, and this is fun to look at. Let's just watch. This is the image of the entire focal plane, and then when they begin to move, they look like this. And you can look closer. It's pretty neat. They're all moving at the same time. This actually was a clip from a planetarium show we made for DESI. Our own Claire Lamont somewhere directed this. And sometimes you can actually see this entire show in our planetarium. So our group here was tasked with actually orchestrating this whole dance and making all the sequence of readjusting everything as efficient as possible. That was a lot of fun, and Anne and I really enjoyed doing this, but it was also pretty exhausting. So by the time we got it all work, the day of first light, you see everybody in the control room celebrating. One person looked particularly tired, but he was still extremely happy that this all worked. Now look at the date, the end of 2019. That's just a few months before the start of COVID. That, of course, was bad for many things. It also delayed our survey, so we couldn't get going for a while. So we finally got running, and then this happened. In June 2022, the Contreras wildfire burned over the Kitt Peak Mountain. Here you see two pictures, the fire approaching the observatory. The green line is not a lost observer trying to find the entrance to the dome. This is actually the flight path of air tankers trying to put out the fire. It actually got worse. We were all staring at these images at night when we switched to infrared. You could see all the glows, and you can see it's really approaching the telescope structures. Okay, tense moments, and then this happened. We lost all communication, power went down, and for hours we had no idea, do we still have an experiment? Do we still have an observatory? And it turns out the next day when we saw it again, the firefighters did an incredible job. They actually stayed inside of the Mayer Dome as the fire swept over the summit and protected all the equipment. So we are truly grateful for their effort. That was amazing. So these things happen when you have an experimental program. We got back on Sky and we started our survey, and we actually were really, really successful and very efficient. And we were then able, on schedule, to produce this, the largest map of the universe. And this is a slice through this map, every single point measured with DESI. And as we go through this, this is the data we measured. So what do we, oops, I turned it off again. What do we do with this? Remember, our program was to measure the expansion of the universe, and we're going to slice the universe into number of segments in different time in the history. This is one of them, and you can see the structure. And now our goal is to take this and to find the evidence for the standard ruler by looking at all the pairs of galaxies. Again, I make this sound pretty easy and straightforward. It is not. It requires, again, many people, very dedicated, working on this for years, and then this is what we get in the end. So we slice our map into into 7 segments. If you look at the top, the look back time, this is how far we go back towards the Big Bang. We cover 10 billion years. We cover almost the entire history of the universe. And you can see in each of these 7 slices, we have a very strong detection of our standard ruler. So we can measure it. And then the way the plot is set up is that the expectation, the standard model, is the horizontal red line. So our data, if the model is correct, should all fall on this line within the error bars. Now that looks okay on the right side on the old universe, but if you get more to the left side, they all look off. They're all a little bit below the line. So what's going on? It becomes even more obvious when I plot the data differently. So this is the same 7 data points. The left 2 are 2 different ways DESI measured this, and the right plot is a measurement from the supernova survey, from the Dark Energy survey. And again, the expectation is that black line in the middle. Now the points are close, but they're really not on it. Remember how well it worked for the plot from the cosmic microwave background? That's neither as close as this. So something might go on. So maybe we have to do something to our model to explain our data. And we did this, and maybe it's not the cosmological constant. Maybe dark energy is not constant over time, but maybe it drops a little bit. It's 10% less now. And if we do this, if we put in a new model and we fit it, it looks like this. Now, this is a much better fit to the data. And certainly without anything else, we can state that the DESI data clearly prefers a model where dark energy is allowed to change, to describe this data. This becomes even more obvious if I plot this in a slightly different way. So I didn't talk about this, but we use a parameter, we call this equation of state, to describe the components of the universe. It's basically the ratio of pressure over density, comes from thermodynamics, and one can show that for the cosmological constant, that value W is -1. And then what we did to allow it to vary a little bit, we just did a simple mathematical trick. We added a second term to it that can vary with time, or redshift, which you know is related. So that's what we did there. So we now have 2 parameters, W0, the constant part, and WA, the time-dependent part. So now the standard model, our lambda CDM model, is clear. W0 is -1, WA is 0, constant. That means the red star, that's where our data should be. Well, not quite. That's what we measure. This is the same data in this representation. Our central point is right in the middle of that blue, dark blue ellipse. So this is not confirming the standard model. And we need to quantify how different the two are. And for that, we go to a quantity we call the significance. The significance between those two is 3.8 sigmas for this particular data set. Or in probability, the probability that these are the same kind of measurement is 1 minus this percentage, so 0.01%. Or in real life, if you want odds, the odds are 1 in 14,000. I think we would all take this bet. But in science, we have learned to be more careful. We have seen many 3 sigma effects to go away with more data, with newer analysis, with different methods. So we are not calling it the discovery yet, but we're calling it a strong hint. And even for this, before you go public, you need to be absolutely sure that the data is correct. So we did all these studies. We looked at different data sets. We sliced the data and eliminated some parts of it and see how it works. So in all of those, the significance changed around, but the central value stays the same. We looked at previous data, and it's all consistent. So after all of this, we decided to go public and to release the results last spring, and the reaction was overwhelming. Every major news outlet picked up the story. By now, the DESI papers have some 1,700 scientific citations. And there was one really nice article I want to feature here in the Scientific American. It didn't mention me or my group, but remember the cat that was trying to chat with the observers? She was featured, and they actually claimed she was accidentally triggering some of the exposures. I cannot comment on this. So, where do we go from here? Clearly, there's an enormous buzz in the community. 700 citations speak to that. Many theory papers have been published. I'm not going to talk about any of these ideas. I'm much more excited about the right side. As an experimentalist, we are going to get more data to pin this down. DESI will become DESI 2 and will run until 2035. The legacy survey of space and time, LSST, is starting right now. at the Vera Rubin Observatory. That is an updated version of the Dark Energy Survey, which is an even bigger camera. And then to measure all this stuff from space without the nasty effects of the atmosphere, at the end of the year, we are launching the Nancy Grace Roman space satellite. So we will get more data to figure this out. But what is really exciting for somebody at this university and in CCAPP is that our groups are heavily involved in all these missions. So there will be more results and more answers. And let me just end here by thanking all of you. Well, yes, for coming here, but also for the general public support for fundamental research. We couldn't do these measurements without your help. Of course, our collaborations, I thank all the members from DS and DESI who worked endless hours to make these results possible. Thanks, Christine, for the help with the demonstration. And of course, thanks to the incredible cosmology team here at Ohio State. Okay, that's it. Thank you. Thank you.
Okay, so we'd like to offer you a chance to ask Klaus some questions. There are 2 microphones where you can line up, or if you're stuck in the middle or have any other reason you can't get to a microphone, you can raise your hand and we'll try to get to you. But let's go ahead and start. Hard to see anything. Go ahead, sir.
All right. I have a question, obviously. That's why I'm standing up. Do you know if the Milky Way is located in one of the peaks or one of those sound horizon rings? Or do you have no idea?
Oh, that's a great question. I don't know if you heard. Can everybody hear the questions? I don't have to repeat them. So I showed you that galaxies form preferentially in the peak or at this outer shell, the sound horizon. And he asked whether the Milky Way is in one or the other. I honestly do not know. I do not know.
Fair enough.
I actually don't know if it's known. Sorry. Good question, but I don't know.
Yeah.
Go ahead, sir. Yeah.
I was absolutely thrilled to hear your background where you switched from more in the particle physics to cosmology. In the late 80s, I briefly got to meet Dr. Robert Moon, who worked with Oppenheimer and Einstein on the Manhattan Project, cyclotron. And he devoted the last few years of his life, he said, to quantizing time and space using Platonic harmonic nested solids. Somewhat similar to you, maybe not as detailed, but I was thrilled to see someone who shifted from one field to another and saw a link between them. And that's all. Thank you.
Thank you.
Thanks.
Thank you for that.
Go ahead, Miss.
Thank you so much for the presentation. So my understanding is that both JWT and the observatory, they're both measuring BAO and to calibrate the standard ruler. So can you elaborate a little bit more regarding how do the 2 telescopes collaborate and can contribute differently?
If I understand you correctly, we are all measuring more or less the same stuff. Are we joining forces to analyze the data together? Is that your question?
Yeah. So so you can also measure the the kind of BAO from James Webb.
Yes. So there's a mission I didn't mention, the James, the Webb Space Telescope, that is already out there. It's a successor to the Hubble telescope. They are going to provide information that is valuable to the work we're doing here, but their main mission is something different. They can, with their instruments, look extremely deep, meaning to the very early universe, and see the first stars and the epoch of reionization that I didn't mention to it. So that's what they do. They do some measurements that are related to this. So they did, if I'm not mistaken, measure some of the dark matter distributions with the same technique. But they do this at a very small scale. They don't see most of the sky. But yes, all these experiments work together, and the data is shared in some way or another, sometimes only after publication, but yeah, that happens.
Can I ask a clarifying question?
Yeah, go ahead.
So like, would you say that like JWT like mostly measures like the earlier universe like that are further away from us, like whereas like maybe DESI focus more on the closer universe?
Yeah, you can say it this way. The range for the distance we use redshift, so the range DESI measures is the redshift from small redshift to maybe 2, maybe 3. And James W. Webb goes, I don't know, David, you know, 5 or 6 or 10 even, I don't know how deep they go, but yes, they go to a way further earlier universe, yes.
Okay, so we have a question over here. Go ahead.
Thank you for a fascinating presentation. A practical question. How will changes in federal funding of research affect the longevity of the projects?
Oh, yeah. How much time do you have? So we were, in the very first slide or the second slide, I told you that people moved on and these telescopes became available. This is too strong, but let me just say it this way. We basically saved them by giving them a new life to do this stuff. Now, the Blanco telescope in particular is in jeopardy again. This Dark Energy survey is over. The camera is still working, it's beautiful, but right on the next mountain, a brand new observatory is taking over. So we have plans what we can do with the Blanco, and we are presenting those to the funding agencies. But I mean, there is an enormous pressure to get money for these things. Yeah. So these two observatories with these two experiments were arguably the most prolific producer of science results in this field for the last decade or two. So clearly the funding agencies got their money's worth out of this.
Okay, so let's take these 3 questions and please try to keep them a little bit short. Go ahead, Mr. Lee.
Oh, there.
All right, thank you for the nice talk today. When you show the Hubble parameter, it seemed like that the speed of the galaxy moving far away from us really important. And my question is that, like, how do you discriminate the effect of the universe expands versus the effect of the galaxy is actually moving? I mean, so when you show the balloon picture, the galaxies were just fixed at the surface of the balloon. But in reality, I think it will definitely is also moving in the universe. So how do you subtract the effect of the galaxy itself as really moving?
Okay, so there are a couple of details to this answer that I didn't know, that I didn't include in the talk. First of all, we have the expansion of space. Sometimes we call this the Hubble flow. That's what I talked about. Then all of these objects, all of these galaxies have their own velocity on top of that, usually smaller. That we call that the peculiar velocity. And we can actually see those and measure those. So if they are sitting in a big dark matter halo, they are falling towards the center. That's this peculiar velocity. So that's this velocity. And then you asked why we know that the space is actually expanding. That we do know with a little demonstration I showed you, because the way how it affects light. It takes the light waves and actually stretches them out. And that is how we know that space is expanding.
Okay, so let's just go ahead and jump over here, please.
So I'm always interested in how science is working sort of in the back room. When you were talking about the data was coming in showing that the expansion of the universe was accelerating instead of decreasing, how many advisors were telling their students to double check the results? And I mean, how did that really proceed? I mean, I'm sure there was a lot of disbelief.
I have a good answer for this. They actually wrote a book about this. There is a book, what's the title? The 4-Degree Universe or so. There's a book about this race, I said they did it independently. There was actually competition between those two teams. And they competed with each other to get to this result first. And they wrote a book about it that I can look up the reference for this. Both teams got rewarded with a Nobel Prize, so that worked out.
Okay. Last question, go ahead.
Oh, hey. Hello, doctor. Thank you. That was great. I wish I was smart enough to understand the whole thing. It's like eating good food with a runny nose, you know. But there is one thing. When you showed the charts with the isotropic BAO,
yes,
those charts, and you talked about how at first it didn't, after we got the first data back from DESI, and you showed that it didn't match the data. Can I get this higher?
I hear you, yeah.
Okay. And you showed that it didn't match the initial data, and then you talked about the adjustment factor.
Yeah.
How did we determine that adjustment factor? Isn't it, because that just set off red flags in my mind because we changed the model after seeing the data.
That is true. We did this, but we also, I don't know if I can find the slide real quickly. So the way we found the amount of evolving dark energy we needed is by taking the model and applying it and then fitting these two parameters, WA and W naught, to get the best fit. That is the red line. So yes, we had the data. We were setting out to prove the Lambda CDM model and the expansion history of the universe, and then we got this. Now, that's okay. Then we need to adjust our model, our theory, because the original one does not explain the experimental data. So that is absolutely okay, and this is what we got.
Okay. Thank you, doctor.
Mm-hmm.
Okay, so I'd like to conclude this event with three things. One is, first, thanking Klaus for first a wonderful talk, and also, go ahead. "20 years of outstanding contributions to this science and to our center. And the second thing is if anybody would like to talk about the great things that we could do in the next 20 years, I'd love to talk to you. And a great way to do that is at the reception right now. So thanks everybody for coming.